Today I'm going to be talking about alignment and atlases in the Affine software package. So I'm going to start off talking about what we mean by alignment and why do we want to do it. So what we want to do with alignment is we're trying to bring two objects into some kind of correspondence. And so this idea of correspondence is where we have an XYZ location in one that corresponds to an XYZ location in another data set. And so we're going to do that for lots of different reasons. We're going to do it across time when we do motion correction. We're going to do it between our API data. It has our functional signal in there to our anatomical data. We're going to do it maybe for longitudinal studies. We can compare data maybe across scanners. And we're going to put all of our data into some kind of standard space so we can compare all of our subjects together or even with subjects from other studies. And these are the software programs that we have available to do these kinds of things. We'll spend some time talking about 3D Val Rig. So that's for motion correction. This does a rigid body correction alignment to some sort of base data set. We can also use 3D warp drive and add auto Telerak. If we're aligning data to a template, those do Affine transformations. We can use 3D Q warp and auto warp, and now at SS warper for doing alignment non-linearly to a template. We'll talk about what that means. At SS warper is a very new package program, and that one also includes skull stripping as part of its procedure. We use 3D delineate, which has a variety of cost functions to align data across modalities. And then we have align Epi Anette.py that calls 3D delineate, and it's a general alignment script for that. Most of you will probably not be using any of these software programs by themselves. You'll probably use affiniproc.py because it will call the appropriate programs with the options for you. And we have other things for aligning slices and even for images. We have a plugin in the Affine GUI. And yesterday I showed you where the plugins were hiding, and there's a nudge plugin, and the nudge plugin lets you manually move one data set over another. Everyone thinks that this ought to be a kind of gold standard, that if you just align it by yourself, that it would be good enough, but it's almost impossible to do this manually well. The computer has infinite patience and will try every possibility, but we don't. And finding just the right combinations of rotations and translations is really hard for us. So it's good for getting a rough approximation, but it's not good for actually great alignment. If you know that your data is rotated by a certain amount or translated, you could use 3D rotate. We have also 3D warp. You would use 3D warp for matching obliquities between data sets or applying a specific transformation. One of the first procedures that we do with data sets that come from multiple scanners is we will align the centers of the data set. So to give it a good starting point, we want to put the center of one data set over the other, and so we can use add align centers or even 3D CM to align the centers of mass. If you have specific regions that you want to align, specific markers, you can use 3D tag align and mark off each point that corresponds across multiple data sets, and it will compute an affine transformation to match these data sets together. Okay. So that's just a kind of overview of some of these tools. We'll go into some detail for some of these. Okay, so how are we doing it? There's a little description here of how what we're doing with these transformations, but I'm trained as an engineer, and I like flowcharts. So I prefer to see this more diagrammatically. So this is what we're doing in almost all of our alignment programs. We're taking some data set that will do some sort of pre-processing, and we'll mask that data set, compute a weight for all the voxels, and then we'll calculate some kind of initial cost for it. And if we use this option called 2-pass, which is basically code for saying let's guess a lot of different options, a lot of different parameters. We'll do all those guesses separately, and then see which guesses work out the best. And then we tweak the parameters in the process called optimization. And with each tweak, we transform our data set, our source data set, to match our base data set, and we interpolate into the grid of the base data set. We measure a cost of that alignment, see how well those two data sets match, and if the cost is less than some tolerance, then we save the final data. Otherwise, we repeat this loop. It's pretty simple. All right, so what do we mean by the cost? Well, if we've got two images and we want to calculate some cost of alignment, one of the simplest ways is to just look at the difference. Okay, just say, how different are these two intensities? So let's say my hands are two images, and I want to see if they're aligned. Well, they're aligned when they're roughly about over each other, right? And so we'll take the intensity of one minus the intensity of the other. But we'll do this in a little bit more sophisticated ways. We'll square the difference because we want to look, it doesn't matter which direction it is, so we just want to get that difference. We'll square it. And then we will apply some sort of weighting system. So higher intensity voxels will contribute more to that cost than lower intensity. That's one way to calculate a weight for it, and that's the overall cost function. It's a weighted least squares. And there are lots of different ways to calculate cost functions. This way is good if you have two data sets that are very similar. They have similar intensities. So both of them T1 SPGR or both of them are API data sets. But it's not good if we're matching two different kinds of data sets. In that case, that system doesn't work. And we'll talk about alternatives to that. And when we put the data onto the grid, we've got choices on how we interpolate our data too. So there are Fourier interpolations, linear interpolations. This data has to be moved, so we have to find our source voxel and put it into the new location. What we do is we pull from a set of sources. So we say the location in the original data set that goes into our final grid is going to be at this location, and we'll get an interpolation of the voxels around it. Okay, we can do it linear, cubic, quintic, heptic, all different kinds of ways. Okay, so for the weighted least squares method, this is done we use that method with 3D Val Rig and with 3D warp drive. Okay, and we're going to do that with 3D Val Rig. We're doing that for motion correction. And yesterday we looked at how we see motion in the graphs, in the images, how to find it. And this is an example of what motion actually looks like. Yesterday we looked at a kind of synthesized sample. And motion in an API data set looks like a striped pattern very often. As the person moves out of the image where they were originally acquired, the intensities are changing. So things aren't in the same place. And when we look at the results, we'll see rings of activation and deactivation. So things so around the ventricles, you'll see high activation and low activation. You'll see it around the head. So these are clues that you still have some motion in your analysis. The program 3D Val Rig will do this motion correction for you. And it works with 6 parameters. So it has 3 translations, shifts in the X, Y, and Z along those axes, and then rotations about each of those axes. And then we have the program 3D Warp Drive, which will extend this, and this has got 12 parameters. So besides the translations and rotations, we've added 3 scaling factors and 3 shearing factors. So scaling is just an enlargement or shrinking around each of the axes. And the shears are kind of sliding. So so those are those 12 parameters. These make up the 12 parameters of what's called an affine transformation. And these are applied with just a single matrix multiplication, and it's done in the same way for every voxel in a data set. All voxels are treated equivalently. This has advantages and disadvantages, and we'll see some of these. Okay. So how do you use 3D Val Rig? This is an example command. 3D Val Rig, you give it the base sub-brick that you're using, the kind of interpolation that you want to use, whether you want to have any zero padding, additional zero padding around the data set. So zero padding is adding slices of zeros around a data set to allow for rotation. So if something is tilted a lot, you can add some more zeros to accommodate for that rotation out of the data set. Mostly you don't have to worry about it, but in some cases you will. The prefix, this is standard across almost all Affine programs have a prefix. And this describes the output. So our output data set will be called Fred1 EPI VR plus a ridge in this case. If you wanted a nifty data set, you would add after the VR, you could put .ni or .ni.gz, and it would be saved as a nifty data set, and then you could bring it into some other software program. Okay, and then here we're saving our motion parameters as a 1D file. And we're going to use that in our regression as a regressor of no interest. And this is our input data set. So this is a pretty typical format for an Affine command in general. So lots and lots of options. There are a lot more options that I haven't talked about. Those are available through the help, of course. Okay, so in general, we don't use heptic. I think the default inside 3D Val Rig is Fourier, and we don't actually recommend that. Generally, cubic or quintic is what we recommend. Fourier interpolation generally has a ringing artifact, so we try to avoid using that. But that's something to be aware of there. Okay, so we have some more examples there. Now, if you have multiple runs of data sets, then you could align your second run to your first run, and maybe the subbrick number 4, the 5th subbrick in your data set. And this is that you'd continue on through that. Now, Affine Proc will do all this for you, so you don't generally have to do this on your own anymore, but this is what it's going to do, something like this for you. Okay, and then you can plot the results. These parameters, this Fred2 VRD file, you can plot that over here with 1D plot. This takes this column of numbers and plots them out with and because you've said it came from 3D Val Rig, it knows the labels, and it shows that you're giving, this is your anterior posterior translation, right left translation, inferior superior, and then the rolls, the rotations about each of the axes. So yaw, pitch, and roll. These are from airplane terminology, and this is what those mean. And so you can see by looking at the plots that you'll have peaks at times of motion. So here we have one around 160 seconds where the subject jerked their head up. And generally you'll see this as a rotation on one of the axes here. So here's around the right to left is what we typically see. Okay, so we call it motion correction, but we don't actually fix anything. We're not fixing the motion, we're kind of mitigating the whole situation. We fix the data before and after the motion, and we tell you where the motion happened so that you can put that into your regression. Because the data is gone during the time of the motion. You know, part of the subject has moved, they're not where they ought to be. We don't have the data that we want. So we just say we're going to end up censoring that. We're going to remove that from our data set. And you have to consider this when you're designing your experiment, how your motion will interact with your design of the study, the linear regression. So if you have people exercising or signing or gesturing in any way with every stimulus, you have to consider that, because that's going to be motion at the time that you're interested. We did have one of our users, she decided she had an experiment like that, where 3 years later she decided she would finally get back to analyzing that, and with somebody signing at the time with each stimulus, and it was uninterpretable because you just have so much motion occurring for so long. Now, if you have a very, very short motion, and the bold signal continues on for 15-20 seconds, then you can extract the rest of it. You can say, I don't want to look at the beginning 1-2 seconds, but I'll look at the rest. So it is possible, but in this case there was something like 10 seconds of motion, difficult to do anything about it. It also says, look at your data as soon as you can get it, try to analyze it as soon as possible. Okay, this is an example with a macaque where 3D Val Rig didn't work. So you can see here we have the original data set, and there is some motion going on, and it turns out, so the experiment was designed with a juice stimulus. So, and monkeys love juice. So they would, you give them juice and they get all excited, and of course their jaws are moving too. And 3D Val Rig doesn't know the difference between jaws and brain. It just looks at intensities, and the jaws are very bright, and so it aligns, it takes into account the jaws. But if you mask off the jaws properly, then you can get a corrected image. So these are the curves at roughly the same voxels. So that's motion correction. But if you want to align data from across two modalities, so we'll consider anatomical data sets and EPI data sets, two different modalities, then you could use, you need another kind of cost function. So we have this program 3D delineate, which can compare data from different modalities. And it does include a least squares cost function, something like 3D Val Rig and in 3D Warp Drive. But it has a whole set of other ones. We have mutual information and normalized mutual information. These are the cost functions that a lot of other software programs use, this mutual information idea. And we have the Hellinger metric, which is the default in this program. We have correlation, various kinds of correlation. And we found that these last two are the ones that we need the most often. So this is we use the local Pearson correlation, which is a Pearson, which is a simple correlation, but it's normalized by small neighborhoods around the brain. So we divide up our data set into 96 different volumes, and and say each of these dodecahedrons inside the brain is correlated with the corresponding data set, the other data set, and calculate that correlation. And what we do is we take the negative of the correlation. If they're negatively correlated, that's what we're looking for. And the reason we do that is that in EPI data, we're looking for bright CSF. So we're gonna base our alignment on the CSF signal. So look for bright CSF matching dark CSF in the T1 weighted data set. So to get that opposite pattern, we're going to use that negative correlation. And we wrap this into Align Epi Anette. This will call 3D delineate for us. It creates a weighted EPI data set that has a maximum 90 percentile on your EPI data. It picks one particular sub-brick to use as your base and aligns the anatomical data set to that. And if you ask for the reverse transformation, it will calculate the EPI to anatomical. And it will combine motion, it will call 3D Val Rig for you and do your de-obliquing. It will match obliquities between the data set, and it will bring you to standard space if you provide it an anatomical data set that's in standard space. Okay, so here we've added an option called -add edge, which will show us the edges of our anatomical and our API data set, and we found that this was the best way to look for alignment between these two kinds of data sets. Okay, so this is the same data set we looked at yesterday in Affine data 6, Affine, the anatomical data set. And for years we looked at this and we said they were acquired close together. We aligned to the closest DPI data set, and this was okay. Visually it looks about right. But when you start to look at the details, you see it's not quite right. So let's see if I can convince you of that. Okay, so this is our original data set. The EPI data has these cyan blue edges, and our anatomical data set has these purple edges. And where they overlap, the cyan and purple, we show it into a kind of magenta color. And you can see that these edges are not, they're sort of aligned, not too great. But let's go down to the post image, and you can see that it's not perfect, but we have a lot more alignment. And you can see this even just with the underlay comparison, that it's a lot sharper. So we found this is a good way to check for alignment, is to look at that kind of contrast. Are there any questions?
If you're going to use, say, affine transformations here, is that necessarily relevant? How are you going to?
Well, these are affine transformations, so you're aligning between the EPI and Anette with an affine transformation. We don't use nonlinear between these two because they're roughly in the. Well, I'll get to. There's a case where we do use nonlinear, so, but mostly we don't. Okay, we also, besides the add edge script, we have the @snapshot Val Rig, which will show you the edges as they are. It doesn't do an alignment for you. It just shows you the edges and creates a similar kind of display. These are colored a little bit differently, but it creates a nice montage for you, and it will. You can put this as part of your scripts as a kind of quality control. We have this little viewer program called AIV, so you can use that to look at your JPEGs and PNGs and whatnot. Okay. So yesterday in the Affine interactive class, we looked at lots of different things for visualizing alignment. This is a really important part of alignment, trying to figure out if it is right, because no matter what cost function we devise, your data may not agree with it. So you have to go in and look to see if it actually is aligned. So for motion, looking at the graph across time, or even the image across time, will gives you a good idea of motion. We saw that you can have multiple controllers and look at the crosshairs for a very rough view. Overlays, overlay opacity, the toggle of the overlay and the underlay. I didn't show you one thing, these 4, 5, and 6 keys, and I think that's worth showing. So I'm going to take a quick break out of this. You may want to do this too if you have your laptops ready. I'm in the Affine data 6 Affine directory. I'll start Affine. And I'll change the overlay to my EPI data. Okay, and on any slider, you can click the any image viewer, click the 4 key, and you see that you get this kind of slider at the top. See, and you can drag that back and forth. Okay. So that's with the 4 key. 4 key brings up that slider. If you hit any other number, I'll do the 4 again. You can turn that off. If you hit the 5 key, you get that slider. You can slide the image up and down. That's with the 5 key. Okay, so turn that off with the 5 again. Now the 6 key, this merges both the overlay and underlay into the underlay grayscale. So this is the 6 key, and so you can it's like a phantom EPI data set. And you can do this. This is not just for EPI to anatomical alignment. It's for, you can look at how well your data set matches a template. You can look at two days of scans against each other. So a lot of different uses for it, not just for EPI anatomical data sets. Just to remind you, the E key, that E key, combine it with a lower opacity, shows you a quick way to get an edge display. That was the E key for edge enhancement. And that's a toggle. The O key turns on and off, and the U key is an underlay toggle.
My overlay is gray. The other ones are still green.
So you may still have the 6 turned on. It's interesting that you can combine the 6 with the edges.
But the first time I turned the 5 on, it also went gray. Not green.
Yeah, so everything goes to just underlay when you have you use these 4, 5, 6 keys. Because it's a little bit confusing to add colors on top of this. It's made to just merge 2 images without color. because they're supposed to be similar in some way. So this is with both the 6 and the E. That is allowable there.
Only my 6.
Can we get edge for the overlay?
No, there's no edge for the overlay unless you use the @add edge script or the @ss snapshot. Yeah, the snapshot Val Rig. Those will show you edges in your overlay. But it's not built into the GUI. You have to run a script separately that creates edge data sets for you. All right.
With both overlay, E should just give an edge, right? 'Cause
Yes.
Basically,
Yeah.
only my 5 key did anything. So.
Okay.
Yeah.
There's also a checkerboard that you can get with the 3 and the number key. This is not great for EPI data sets. If you have 2 anatomical data sets, 2 data sets that you think should be exactly the same, then that's good. Otherwise, it's not across 2 data sets. It's just 2 different modalities. It's confusing. So you can see we have a lot of different choices for how we can visualize 2 data sets and look for whether our data sets are aligned well or not. Now, align Epi Anette usually works between the EPI and data sets and the anatomical. And I say that usually because it worked on 90% of the FCON 1000 data sets, which came from 25 sites around the world, and it worked for 90% of them. It didn't work for a couple of them. And this is where the data set contrast was not as good. And there are some reasons for that. What we recommend is a few things. Okay, if you have, well, you can change your cost function. And actually, the one that works at best is not the original local Pearson correlation. Probably our most robust cost function is the LPC plus ZZ cost function. And what that does is it does a first pass with a combination of lots of cost functions. So it adds a little bit of normalized mutual information, a little bit of least squares, and a lot of local Pearson correlation, and finds a kind of combined cost function. And then from there, it does a final calculation on local Pearson correlation. So LPC plus ZZ seems to be a better option. But it's also good if you have worse contrast. If you have really terrible contrast, because you remember that this is relying on CSF being different than the rest. So CSF has to be bright on your EPI data set and distinguishable from the other tissues around it. If you don't have that, then LPC won't work well. So you need to try something else. So you can try normalized mutual information, works well for that. LPA is a good cost function for that. So you can play with your cost functions. If they start off far apart, so most of the time when you have anatomical and EPI data set, the scanner will give it to you in correct coordinates. If you get it from somebody else, it may have gone through a procedure or several pipelines someplace else that has lost that information. So you may not know, the coordinates may not be correct, and so you may have to align centers first. For some reason they are far apart, or they're just plain wrong. You can use, we have Big Move, which does that 2-pass option, and then we have Giant Move, which allows for a fairly large range of translation and rotation, for up to about a 45-degree rotation. And then we have Ginormous Move. Ginormous adds in a center alignment, so we can put the centers over each other before we start. If you have a lot of edges that are much brighter than the rest, you can use the dash edge, which is a different procedure. And the LPA cost function works better there. If you have other questions like stroke or other kinds of lesions, you can ask us. We can give you scripts that have been developed specifically for that and some tips to what to do for that.
Question. So why have a big, giant, and ginormous move? Why not have an algorithm?
Because most of the time, the data doesn't need to be moved a lot. The coordinates are about right. There's just a very small amount of alignment that has to be done. So
Time. It just takes time to do all that.
and it does make it slower. It does make it slower, but if you expand the range of parameters that you're looking at, it's more likely you can go wrong too. So most of the time, most people will not need to use any of these options. Okay, when we introduced this, one of our users, Mike Beauchamp, he sent us this data set and said, your new alignment procedure doesn't work. Look at this. And we said, oh, wow, we thought we tested out well, but it looks like there could have been something wrong. And he showed us this anatomical data set is over an EPI data set. Now, as you have seen here, we generally do it the opposite way. So that was a clue that there may have been something, a different way of looking at it. That's either we didn't take it into account or there's something wrong there. So when you get this anatomical data set has been skull stripped and it's sitting over our API data set. But if you look at the original anatomical data set, you can see that for this particular subject, there's a lot of CSF around the brain. And that's what we're seeing here. So the alignment actually did work because we are aligning that CSF to that CSF. So in the end, the procedure was correct, and it's just by looking at the contrast of the CSF on the original data sets, you can see where things are. Okay, some more special cases of alignment. We have Helen Mayberg, who used to be at Emory, with Justin Rajendra, who also used to be at Emory, and he's now working in our group. They were doing DBS, this deep brain stimulation, putting the electrodes into the brain. They needed to get these electrodes within a millimeter of their target location, and this is for treatment of depression. They have pre-surgical MRI, they have CT, they have PET data, they have DTI data, and all these things had to be aligned together. So we used Align Epi Anette to do that with some tricks. So to align CT to T1 data, for instance, the T1 data, the skull in T1 data is just that thin black layer, that thin dark layer between the meninges and the skin. You can see a small layer that is the actual skull. And by reversing our T1 data set and then aligning it to the CT, with a rigid body transformation, we could align these together. We use the same trick with ECOG data, which also has CT and T1 data sets. And we have this as part of the ALICE pipeline for dealing with ECOG data. Some more unusual data sets. This is manganese enhanced MRI. This is in rat brains. So we have data, manganese chloride is injected into the rat brain. We can see neuronal transfer over a day. So this is a kind of a day scan. With every we have different hours that we've looked at that we take the scans, and it enhances as it goes through the tissue. So in this case, it was done through the nose, basically, and then it travels through the brain, and we could see it over the course of the time that during the scan. And because there was so much enhancement, the regular procedures didn't work, and we use the dash edge option, and then accounted for the small voxel sizes with the rad align option and LPA cost function. So a small script using the same align EPI Anette. So align EPI Anette, although it's called align EPI Anette, we don't just use it for EPI and anatomical data sets. We can use it for all kinds of affine alignment. We have a GUI for align EPI Anette. It provides a very limited set of options, a couple cost functions, but allows you to try that out. But most of you will be using affine.py to do your alignment, and you won't have to deal with the small options in align EPI Anette, and it will do it as part of your processing. And these are the options you put in there. You use the align option. There are various options of which to align in your Val Rig. You can align to the last, or align to the first, or align to the minimum outlier. It doesn't really matter much which one you use. Just use one that doesn't have motion in it. It would be a good idea. Okay. This is a typical series of transformations. We're going to align all of our data. So all of our data gets aligned, our API data gets aligned to one particular sub-brick of the API data set. That gets aligned to an anatomical data set. That anatomical data set gets aligned to a template, and then we can use the atlases from various spaces that are associated with that template, and ones that we can get to from the space of that data set. So we know how to, if it's an M&I template, we can use an M&I atlas directly. And we have transformations to go from Talarak space to M&I, and so we can use those too. And we'll do this across sessions. Now we have a script if you want to remove bias from one session to another. You have two sessions of data, and you don't want to have one as the one with less motion than the other, or less alignment done to it. You can create an in-between anatomical data set, and it's similar to the previous slide, except we've created this in-between anatomical, and all the data will be aligned through this in-between. So maybe pre and post exercise, pre and post some other kind of treatment. And you can extend this idea across multiple sessions too.